The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
We've got our first speaker is going to be Dr. Rich Sacchi. He's with the Texas Aggregate and Concrete Association. He is the president, formerly with Latimer Materials. He has a PhD from the University of Illinois. He's an Aggie, which would be A&M in Texas parlance. And he is also an avid cyclist as well, and energetic guy. He's going to be telling us about hot weather concrete specification choices to achieve architectural concrete results. Rich?
Thank you, John, for asking me to come in and speak. It's always an honor and privilege. I feel a little bit like a lapsed Catholic in front of a Catholic Mass because everybody has sat towards the back. And John and I did have a betting pool as to whether or not we would get 10, so unfortunately I had 10, he had a higher number, so I owe John lunch on this one. I was asked to come in and talk about hot weather concrete. As John was alluding to, while I represent the aggregate and concrete producers in the state of Texas, my, we'll call it formal education in the industry comes as a ready-mix and aggregates producer, specifically in Texas. Here in Dallas, my last stint, we did quite a bit of work with hot weather concrete. So a lot of my examples, a lot of the things I'm going to show you come directly from that experience, particularly with the conflicts that arise there. And so I'm going to try to frame the discussion today around where those conflicts come from and point out some real-world consequences of some of the choices and decisions that we make with respect to those. So I'm going to do this in 3 ways. I'm going to first talk about what I like to call the battle of the specifications. If there's any attorneys in the room, and John mentioned when we were recording it, he said for posterity's sake, and anytime somebody records something, I always ask, is there an attorney in the room? Just to make sure. But we wind up with this battle of the specifications or paperwork because one tries to keep trumping over the other one, so I'll talk about that. And then the other thing is, as a scientist, I always want to go back, and the nice thing about ACI is I really can do that here, is I want to go back to first principles that have to do with material combinations and how those directly impact there, and then finally talk about some of these conflicts and how we resolve them. So this is kind of how we're going to set the stage for the battle, is I've got structural code requirements, I've got hot weather limitations, and I've got architectural requirements. And somehow we put these 3 Mack trucks in the same lane together and we run them head first into each other and we say, we're going to expect to have an architectural result we can all live with. Now, this looks very, very nice, these pretty little Venn diagrams, and you're thinking, oh, it's simple. Yeah, we just want that target right in the middle. Easy. Right? Well, let's talk about a couple of those things. First, let's talk straight off the bat with hot weather specifications. And I've listed for you up here the numerous ones that I have seen. Now, while ACI 301, ACI 305 has limitations at 95 degrees, that doesn't mean anybody has to follow that. How many, just by show of hands of all 12 of us that are in the room, how many people actually in here are licensed professional engineers? So we all know from our license, as designers or specifiers, we largely get to do whatever we want. In spite of the code, because we have that one thing called professional judgment or licensure. So the code may say one thing, but we actually can say something else. And here are great examples. Remember I said ACI 305 or 301? Concrete shall not exceed 95 degrees when arriving at the job site? Well, what about ones that say 90 degrees? What about ones that say 85 degrees? Ice shall be used when concrete temperatures exceed 90 degrees. These are all common specification, common language that we see in hot weather specifications. And in Texas, we're used to these all the time. Now, last summer in Texas, we set the second largest record, it was the second most consecutive days above 100 degrees. We in fact set record temperatures, 113, 115 degrees here in North Texas alone. And one of the things that we had the problem with was we honestly could not get the temperature down below 95 degrees. It could not be done by any means. Now, we'll take liquid nitrogen off the table for a second. Somehow people still wanted concrete to their jobs. And allowances got made. And I always tell all the producers during that time period, I said, write that down. Remember this, because next summer in 2012, everybody's going to forget that, and they're going to come back and go, we've never poured concrete above 95 degrees. You remember the summer of 2011? We poured a heck of a lot of concrete above those temperatures. And so far, nothing's fallen down. Architectural specifications. Architectural concrete shall maintain consistent color and hue. That's one of my favorite ones, because my experience has been concrete changes color over time. In-place concrete shall match color and shading of test panels. No fly ash shall be used on architectural concrete. And this is my favorite one. Funny, I should mention the Catholic reference at the beginning, because this is what I like to call the Holy Trinity of architectural concrete. Architectural concrete shall be consistent in color to the test panels as measured from 30 feet away by a 3-person panel composed of the architect, the contractor, and the supplier. Anybody ever been on that job? We have one right here in Dallas that uses that as a method of acceptance for its architectural concrete. Imagine 3 people standing 30 feet away, and I have seen it done with a tape measure, going, okay, let's run down here to the test panel. Okay, come back over here. Oh, whoop, 28 feet, now I'm 30. Yeah, that looks okay. That's the way the project is being evaluated. Imagine being on that job. And by the way, the test panel that was over here, it was poured 6 months ago. So we have these type of specifications. So I've only gotten 2 so far. Hot weather and architectural specs. Finally, we have the structural specs. And these, I think everybody is fairly familiar with. Water-cement ratio issues, minimum powder issues, maximum slump issues. That's one of my favorite ones. Maximum slump of 4 inches for all architectural concrete. Try telling a contractor that who has to pump it. Getting some heads nodding in the back of the room. They've seen that one. Air content shall be 5% on all exposed concrete. Now, I'm just going to give you all a little secret down here in Texas, where it's hot. We're talking about hot weather concrete. In most cases, hot weather issues usually don't coincide with exposed concrete durability issues with freeze-thaw. I'm just saying, in a general geographic sense, it's very odd to see that, but that still doesn't prevent anybody from putting it in the specification. And maximum 20% fly ash. So we're all over the board. So imagine you have these 3 groupings of specifications showing up in the job, and somehow we're supposed to get a consistent product at the end. Now, I'll give you the 4th one here, and this is kind of my first principles. Now, I realize that this is a complicated picture here. I have for you the basic hydration equation of what happens when we take cement and we add water to it. Now, I realize that there's a variety of chemists in the room that are going to start to go crazy on me and go, you can't talk about it that way. You've got to... Let's just, for the sake of argument, say I'm going to add cement and water, and I'm going to get 2 products out of the back side of this. One is going to call CSH, calcium silicate hydrate. We're going to call that the good part. The other part of this thing we're going to call the bad, which is the CH, the calcium hydroxide. We'll get to those in a second. The thing I want to highlight for you is when these two products are formed, heat is generated. That's the exothermic reaction we're all familiar with. This heat, highlight for you here. One is chemically driven. The cement content, the water-cement ratio, pozzolanic replacement, all contribute to that. The other part of this is the structural temperatures. Notice a couple of things here, the curing temperatures. The curing temperature is largely controlled by ambient conditions. My core temperature, huge issue. I get into large, we'll call them discussions. Some people might call them fights. I'll call them animated discussions for the sake of discussion. Is when somebody says, oh, we're concerned about temperature at placement. I said, why? 6 hours later, it's not going to be there. It's core temperature that counts. Well, what's core temperature? Okay, so then we have to start that discussion. The core temperature is largely fixed because it's based on the mix design and the element shape. So this is the basic equation here. Now here's what happens under hot weather conditions. So now I'm actually going to add heat to the first part of this. While the cement and the water are mixing, I'm going to infuse heat into this equation, and I still have some of the things that happen. My set time, of course we all know, goes down. I decrease my set time. My initial strength is increased. From a ready-mix standpoint, we always like to talk about we're cooking the concrete faster. We cook it faster, I'm going to get a burst of strength at the beginning. Now we can have large discussions about, well, what happens to final strength and those type of things. But from an initial standpoint, when it's hot out, I get to drop forms faster. I get to release cables faster. These are real practical impacts. But my final strength, we'll leave that one as a little bit of a rhetorical. But let's go back up here to the structural. First thing is my curing temperatures. Those are largely going to get increased because my ambient temperatures are there. Core temperature, though, interestingly, really is not affected by that because my mix design didn't change. My element shape didn't change. The core temperatures largely stay the same. So the translation here, the takeaway, is that it comes back to curing temperatures are largely impacted, which affects set times, which affect initial strengths. Now, why is all that important when it comes to architectural concrete? It's because of how we choose to manage this and the impacts that we have on architectural concrete issues, particularly the aesthetics. And that's really what we're talking about when it comes down to architectural concrete, are the aesthetics. So what do we choose and how do we choose to manage these things? Let's look at a couple of those things about what we actually control here and where we have control, because in a lot of cases, some of this is misplaced. The first thing we absolutely know we have no control over is ambient temperature, ambient humidity. We don't. Now, you'll see some people, well, under curing conditions, I can control the localized ambient humidity. Well, that's not what we're talking about here. So let's just take, for example, just right off the bat say we don't control the ambient temperature, ambient humidity. But one of the things that we do control. Now, here's the interesting part. A lot of people say this block right here, the temperature at delivery, is where we need to exert all of our authority and control the temperature at delivery, the temperature at delivery, the temperature at delivery. Well, what about all these other things that we actually control over here? I control the water content in the mix design. I control the color admixtures, and I control the powder content. I actually have that under my control, notwithstanding the specifications that we went through before. Now, I'm not a color guy, I'm not a color salesman or anything else, but I can tell you from my industrial experience, if you have a color in mind you want, I can get you that color with any powder combination I choose. Whether it's got 0% fly ash in it, 10% fly ash in it, 20% fly ash, 30% slag, and the remaining part cement. I can hit the color you want. We are that good with liquid and powdered colors now in 2012. All I have to do is tell them what color I want and tell them what my powder combination is, and I can hit that color. We don't have some of the limitations that we had 5, 10, 20 years ago where somebody said, oh, you could only have to use white cement to get a colored concrete. I mean, the other thing is I know for a fact because I've done it. I've done colored concrete with 35% fly ash, and I've hit some of those difficult colors. It's not hard to do. You just have to let people know what you're doing. My point to this is we control a lot more than we think we do. It's a matter of exercising that control. So, let's talk about some of those practical things that we can actually do, because the other part is I've got the visual aspect of architectural concrete, but I also have the issue of managing those temperature concerns that go to set time, strength gain, and some of those things. So here's some of the 4 bullet point list that I'm going to give you on how we look at this. The first is the mix design. Lowest practical cement factor, maximum practical aggregate size. Those two things will help control that temperature. Pozzolanic materials, you've heard me talk about that. Then we go down into the chemical group, set retarders, water reducers, and finally the mechanical group. Now, the other thing I want to show for you is that list. What else is very, very evident with that list, or maybe not evident, as you move down the list? 1, 2, 3, 4. What happens to my cost as I move down this list? This is the least expensive thing to do. This is the most expensive thing to do. This is in order of expense. Now the other thing is, I always tell people, as a concrete and aggregate producer, my job was not to make concrete, was not to make aggregates. My job was to make money. My job was to be profitable. And so in any discussion I always had about the technical merits of something, I had to infuse cost to it because that's the way we make these things. It's about being profitable. So in these particular cases, when somebody says, oh, hey, I want to cool the temperature of the concrete by using ice. Remember that specification I showed at the beginning? Thou shalt use ice at 90 degrees plus? Well, how about if we did something less expensive on the front end? Oh, no, well, we can't do that. Well, okay, if you'd like to write the check, I'll be more than happy to cash it. Well, let's talk about that a second. Let me give you an actual mix design on an actual project where we had this issue. So here's the mix design with the composition of it and the weights here. And I want to highlight for you the ice that was necessary to achieve the 85 degree temperature specification. We had to put in 100 pounds of ice per yard, which meant the initial mixing water cement ratio at batching was 0.29. Well, no, wait a second, Rich. The ice was in, 100 pounds. That's water. Yes, in solid form. It doesn't really count as water because it's still solid, which meant I had an initial mixing water cement ratio of 0.9. Now for the admixture people in the room, they're going to tell me that admixtures work off of wetted cement grains, simplified. How wet do you think my cement grains are going to be on this powder content at a 0.29 water cement ratio mixing at a 10-yard batch in the back of a ready-mix truck? How effective will those admixtures be? Particularly when the delivery time from the plant to the job site was 20 minutes. Do you think that the ice fully melted over the 20-minute time period? I had ice chunks coming out of the chute. And here's the other complicated part. What happens if now you're there mixing, waiting for the ice to melt, and you exceed the 300 drum revolutions? And somebody says, I'm going to reject the truck because you've gotten 301 drum revolutions even though your ice hasn't melted. Now, here's the other issue. Inconsistent mixing, workability, cement admixture, inconsistent slump, inconsistent color. We actually put ourselves in a situation where we got poor architectural concrete results in trying to achieve another part of the specification. those conflicts. This is a very practical example of what happens. So the question always when I show this slide is, well, how did you guys fix this? I'll tell you that one in a second. Hold on to that question. Now, let's go to the other part of this equation. Remember I mentioned the economics? Well, let's talk about that. Each 500-yard placement for the 85-degree temperature limitation costs $6,000 in ice. Over the course of the job, it took $360,000 in ice, frozen water. And here was the question I asked at the end of that project. Owner, when you spent $360,000 in ice over that placement, did you get better concrete? Did you get stronger concrete? And more importantly, did you get things that look the way they should? When I teach an ethics class to engineers, I always go back to the first principle of our canon of our ethics, which is protect the public health, safety, and welfare. Everybody always gets concerned about public health and safety. Welfare is the interesting one, because are you truly being ethical when you design something to spend $360,000 of the owner's money and you have trouble answering these questions? Won't get into that one a little bit, but my point is, in this particular case, we spent an inordinate amount of money on this project to achieve a temperature requirement in hot weather, and we weren't really sure if we met the design goal here other than that it looked the way we thought it would, because it matched the test panel. Interestingly, though, when we made the test panel, we didn't use ice and we didn't use 85 degrees. We just cast the test panel. So somebody say, well, see, the ice worked. Well, I would like to say I probably could have done all of this and not had to spend the money as well, particularly when I'm rejecting trucks because I don't have my ice fully melted. When it comes to these kind of things here, the temperature and architectural things, one we talked about, it's chemically driven, which means we need to think about things a little bit differently when it comes to that. Let's manage the chemical process better, and we might be able to manage the result better. Let's go back to first principles. The other thing is the temperature specifications or limits that we place on this. These are measurements. And outside of core temperatures at 158 degrees, resulting in delayed ettrinite formation, they're not really an indication of performance. My experience has taught me that concrete is not smart enough to know what temperature it used to be. The slabs that we're standing on right now that are holding this building up, can you tell me that their performance is based on 95 degrees, 92 degrees, 85 degrees, or 108 degrees? Or do you just know that they're doing what they're supposed to and that they made their compressive strength requirement? The other thing is, I've always been in this situation where somebody said, well, you placed that concrete at 102 degrees. It was too hot. Look at this. We're looking at the lab reports right here. 102 degrees, you placed concrete. It was too hot. We had a 90-degree limit on this. Well, I want this concrete torn out. Well, what was the spec on the concrete? Well, it was 4,000 psi. Well, what did the cylinders break? Well, in 7 days, they broke at 5,200. But it was too hot at placement. Well, do you want to tear it out for that? In my experience now, going on 20 years, I have yet to be in a situation where we've torn out concrete because it made strength but was too hot. The other thing is this combination, and I'll highlight for you this one statement. Allowances are more important than restrictions, limitations, or prohibitions. Allowances are more important than restrictions, limitations, or prohibitions. That's how we get those results that we're talking about. Go back to my very pretty Venn diagram and how easy and simple it looked at the beginning. Imagine us being able to talk about those things early on. And I'll finish with this here. Has anybody ever been in a job site trailer having a discussion about a situation that goes on? Next time you're in that job site trailer, look around, count the heads in the room, and add an hourly rate to each one of them. And tell me how much that hour-long meeting cost on something that largely could have been handled at the beginning when it came to the specification issue. My experience with architectural concrete is many of the issues can be headed off at the beginning when you start talking about those conflicts and how we resolve them. In a lot of cases, like I said, the most important thing is the allowances are more important than the restrictions, limitations, and prohibitions. Here's where I can be contacted. If you've got any follow-up questions, thoughts, ideas, please don't hesitate to contact me. I give you all the stuff there. You can also look me up through the ACI registry as well, and I think they're going to use this presentation online. So, thank you very much, John, for inviting me to come in and speak. I appreciate it. If anybody's got one or two questions, I think I've got a couple of minutes. So, thanks so much, everybody, and I appreciate, all of y'all being here first thing Wednesday morning. So, thank you.
What about source variability on flash? That's something that's popping up a little bit. How do you effects of that on color?
Yeah, John asked a question about source variability on fly ash, and one of the issues that not only we're having in Texas right now, but I know in other places can have is changing sources. And that can impact the color, and can have quite a challenge with it, particularly because of carbon content. One of the things that I look at if I had to switch from an F source 1 to an F source 2 is carbon content. The other thing is F versus C, those type of issues. Personally, I try not to change ash sources during the job because of that. Unless I have a significant break. In a lot of projects, I may pour a portion of the structure early on, and I may not get to the next colored portion of that for 4 months. Now I do have an issue because anybody who believes that the cement or the ash that you get 4 months later or 4 months from now is the exact same, it's not the case. And so, in a lot of cases, when I have a break, even then, I'll redo a test batch with the same color and just check it. That's more the art than the science of it. But it can impact it. You just have to watch it.